Hello, everybody. Welcome to EthCC Hack 2022. I'm Bernhard. I'm with Fluence Labs, and we're super excited to be here and to be hacking with you. This, unfortunately, is a pre-recorded and no interactivity clearly. So if you have any questions and comments, please reach out to Telegram or Discord. And also, we're going to be there for the week in person. So any help we can give you there, please reach out. We're happy to do it. And looking forward to an exciting week. Fluence, what is Fluence? Fluence is a decentralized peer-to-peer compute protocol. It's a network and the tooling, where the network actually is not Fluence's network. Fluence basically bootstraps a peer-to-peer open permissionless network, which anybody who operates a compliant protocol compliant node can join. All the tooling, the network nodes, the reference nodes we provide, which you're free to customize, of course. And the protocol are fully open sourced, Apache peer-to-peer, Apache 2.0 peer-to-peer on my mind, Apache 2.0 license, so it's very permissive and very accessible. You've probably seen sort of the many different incarnations of this Web 1 to Web 3 journey, and I think so. I'm not going to get into too much detail in this workshop, but what the important part is that there's an evolution. The evolution is driven by constraints, whether regulatory or market demands, as well as enabled by innovation and invention. And Web3 addresses a lot of the grievances, if you will, we've encountered through Web3 business models we just don't think are particularly fair and sustainable. So censorship resistance, minimized risk of deplatforming, low exit barrier, control over your data, control over your identity. Those are all attributes of Web3 we're looking for to counteract some of the perceivably unfair and concentrated power distribution that's currently sitting in Web2. And a lot of the Web3 attributes are unlocked through decentralization, but it's not just decentralization, but actually through peer-to-peer decentralization. Peer-to-peer networks play a critical part in the decentralization of Web2 and play a critical part in unlocking the Web3 benefits. Just decentralization without peer-to-peer actually does not give you most of those benefits. And if you look at it from a server perspective, it's not particularly difficult to decentralize a bunch of servers without actualizing Web3 benefits. And that's really what we're after. So not surprising, people in the Web3 camp are let's decentralize everything, and with peer-to-peer networks. And we've seen a lot of this happening in financial systems, so crypto, smart contracts, DeFi. And that's probably not going to go away. Well, probably, I don't think it's going to go away, because if you look at all the efforts from central banks looking at digital currency, this is the best model in the journey of e-money over the last 30 years or so we've seen. And of course, it's really the high probability elimination of double spend at a relatively low cost, which is super critical. However, we don't just want to decentralize financial systems. We actually want to decentralize a whole many layers of the internet. Storage, for example, Protocol Labs IPFS Filecoin is a great example of how to decentralize storage with peer-to-peer networks, and to bring innovation to the market, like content addressability, which totally changes the way you deal with data, how you create complex data models using IPLD and all that good stuff. And another aspect is identity, right? I mean, we've been dealing with eGov, digital identity, blah, blah, blah for a long time. Nothing ever really stuck. Then about 4 years ago, 4.5 years ago, serious work started to begun when decentralized identities, verifiable credentials. And just now you really see a lot of coalescing going on. You see efforts like UCAN, Cacao coming to bear, and really changing the way self-sovereignty is expressed, how we can retain control, not just of our data through peer-to-peer type storage like IPFS and Filecoin, but also our representation of ourself and any other secrets we like to represent but not necessarily share explicitly through non-interactive interactions. And another one, of course, is decentralized networking. Networking can be decentralized on many different levels, but probably the most prominent is social networks, right? I mean, you're fundamentally being held hostage by your own data in these walled gardens, whether it's Facebook or any one of them, Google. And you have great alternatives like Mastodon, for example, but you need the network effect. And in order to get the network effect, the people currently locked into these walled gardens need to be able to get their data out. And this may be a generational issue, or it might be a regulatory issue where probably, if I'm looking at it, looking more towards the EU, probably to force some of those walled garden providers to let users take their data out. And once you take it out and you start looking at peer-to-peer decentralization perspective, and you build the right tools, you actually can build these complex data models very easily, very cheaply on decentralized storage. And now it's portable and could be easily consumed by any of the mastodons or subsequent or current competitors in the marketplace. And your data could be synced and could be, it's actually not that difficult to do, even at scale, particularly if you have these content addressability models that come out of decentralized peer-to-peer storage. And of course, the last one is computing. I mean, there's more to it. There are more attributes, but the last big one is computing. And this is, of course, where Fluence comes in. So decentralized computing, the different incarnations, if you will. Most of you are probably very familiar with smart contracts on chain, very deterministic. And then there are decentralized hardware marketplaces, like live periods. So the on-chain compute, as I said, it's deterministic, so there's a lot of limitations. I mean, blockchains are fundamentally introverts, so you need off-chain compute to complement the limitations of the blockchain, which of course has a lot of advantage because you end up with immutability and longest chain through longest chain building, and consensus through longest chain building. And that's a really valuable model, but it doesn't cover all compute. Then in the decentralized hardware marketplace, you look at Golem and LivePeer. LivePeer, for example, you have a very specialized. I mean, LivePeer is very, very powerful, transcoding a video. If you haven't seen it, I'm sure you have. And very, very powerful, actually extremely inexpensive to do. And therefore, a very, very viable option for a lot of video coding demand or transcoding demand. And again, this is decentralization through peer-to-peer with an on-chain marketplace component, which is super, super exciting. But it's still not general compute, which is fine. But where Fluence come in, this is the long wind-up, is general purpose peer-to-peer compute or peer-to-peer based compute. And basically what Fluence wants to enable is any kind of computation using function addressability, which is sort of the equivalent to content addressability, and using WebAssembly on universal runtimes to operate within open permissionless networks. So that's really what the Fluence vision, and this is where all the tooling we're going to talk about and the code we'll see a little bit comes in. So Fluence, decentralized peer-to-peer compute. Time to get a little bit, come a little bit down in the level of abstraction. So on the right here, you see a peer-to-peer network. You have two client peers, if you will. Those are the upper green and lower left green. And could be a browser, could be a node app, doesn't really matter. Those are peer-to-peer clients. And then in the blue are peers in the peer network. Relay obviously is a peer that's publicly accessible, could be sitting in front of peers behind NATs, et cetera, et cetera, et cetera. These peers in what connect together to form the Fluence network are enabled to host WebAssembly-based services. And it's WebAssembly IT, not Bindgen. One can get that a little bit. And that allows you to really have the building blocks for a generalized compute network, peer-to-peer compute network. And these services could be encapsulated any kind of business logic you could possibly express in WebAssembly modules. And that includes actually adapters. adapters to pre-existing capability and resources like your API, microservices, but also to other peer-to-peer networks like IPFS. And we have a full integration with IPFS where you can basically use the tooling from Fluence to seamlessly go back and forth between the compute network, Fluence, and the IPFS data network by extension of Filecoin. So we get a peer-to-peer network, which actually is representing the connectivity among a whole bunch of peers, which are reference nodes that connect to each other according to certain rules, part of the protocol. And each one of those nodes or peers is capable to host WebAssembly modules, which are services which are then addressable and callable and executable on these particular nodes. And when you compose across those different services, you get protocols and applications. So let's get dive down a little bit more, and let's give an example. If our green client up left and low left are browsers, and if our task at hand is to send a message from the upper left to the lower right, by improving upon the text that was input in the upper left, by basically scanning the text to convert relevant characters into emojis, and then to do a spell check. Okay, so basically, if our text is :1 EthCC, and we then basically say, hey, throw this out on network, and before you deliver it to the lower left green client, check the text for emoji injection. So we have an emoji injection service, which would be right here. So we connect from the browser to the relay. The relay then starts figuring out for peer discovery and content routing to this particular service. It may not be a straight shot, right? It could go through a whole bunch of other nodes. Rest assured, there's end-to-end encryption in place. It doesn't really matter if it goes through another node until it gets to the final node. It's all fully encrypted. And then in here we have this service which is now executed and scans the text. In this particular case, it says, oh, we found :1, which means thumbs up, and we replace it with a link to a PNG, for example. Done with that, apply our state change to the text. We now somehow find the next service, which is a spell checker. We get there, again, to be direct. In this particular case, it looks direct, and we now spell check, and obviously we basically go from EthCC to EthCC. And very subtle, but it's a really good spell checker. And then we deliver this to this particular client down there. Great. We also could have another service here that says, hey, in parallel to delivering this to this client, actually save this this very, very important text to IPFS. You get a CID back and do with it whatever you want. Okay, so it was a very simple three-step, three-service example. And so basically what we said, hey, there's a workflow. So I alluded there's a workflow. And one of the things I said before is that all these services are function addressable. So they are addressed over the peer-to-peer network, not JSON RPC or REST. So there are no web servers or app servers here that like JSON RPC on an Ethereum node where you say, hey, blah, 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 go and interact with that server. No. You address the services very particular over peer-to-peer. And this is one of the key parts of the Fluence protocol. And this is enabled by a programming language called Aqua. Aqua is a Fluence invention and basically allows you to compose distributed services in these networks to into protocols and applications. And let's just have a look real quick in how Aqua works, and then we look at a couple other technical details to hopefully explain this a little bit further. Because what you saw here, it's not the typical client server request response model. It's literally a data push model, And that's actually really important because it has an impact on enabling very thin clients and a few other ones that we consider vastly superior to traditional client-server interactions. So Aqua, let's just like have a look at right here. So out there, there's a service. Basically, it's an IPFS service. We wrote in Rust and compiled to WebAssembly that basically extracts parameters from an IPFS document. We'll actually look at this very service in a little bit later in detail. So believe me, it's out there. And we wrote this, we compiled it to WebAssembly and deployed it to one or more nodes or peers, if you will, out there. And by doing this, we end up with a function addressable tuple, which is the peer ID and the service ID. So that service is out there. So what we now do is we basically create an interface which corresponds to that WebAssembly service out there. And this is the namespace. It takes a service ID, which we get. It shouldn't be is, it should be ID. Sorry. And that has this particular function. And this particular function basically takes the multi-address of the IPFS node, which is in every Fluence node comes with an IPFS sidecar. And the CID of the saved documents, basically a bunch of parameters that were uploaded to IPFS, which we now use as function arguments. So instead of using actual arguments, we're using a CID, which is actually, again, I'll show in a later example, actually really cool because you can very succinctly process very complex linked data models. And then we basically just have a function. This is an Aqua function. We call it check utility addresses. And it takes the CID, which corresponds to here, the multi-address, which corresponds to here. And the Fluence peer is, I didn't name this particularly well, but the Fluence peer that has the IPFS sidecar. So this is the peer ID hosting the service, and this is the actual service ID of this IPFS service we use. And we return basically what I call a function address, which is the peer ID, as I mentioned before, and service ID. It's the tuple as a data structure. So now this is so you're on the screen, you're in green right now, right? So you have this script, you have it in some client. It could be deployed on a node, but let's just say you have a client, a peer client, and you sort of throw this out and work, and you're on some relay. And the relay doesn't have to be where you're on, doesn't have to be that particular node where we want to access the IPFS sidecar. So what we're now saying in Aqua is basically on this node, we might be on a different peer, right? But we're just saying on the peer we're on this potentially different peer, create a binding of this interface to this particular service ID, and then execute in that namespace, in the service namespace, this function with those parameters, right? Just like we specified up there. That returns us, in this particular case, a function addressability tuple, which happens to be the peer ID and service ID, and now return this result back to, in this particular case, the source, the originating peer-to-peer client. So it could be from this node, from this node, we go back to the relay, back to the client, right? So if we were just like in that examples, if the service was here, we push the result back to here and then back to here, if that's what we wanted, which is what we did in this particular example. So if you look at Aqua, it allows you to compose these services very, very easily into much more complex workflows, and it actually allows you to program aspects of the Fluence network, and but also seamlessly interact with IPFS network in this particular case, based on some integration work that's already been done and is ready for you to use. So how does that work? How does Aqua work? How does this all work? How do we get this data push model we talked about, and how do we actually find these services, and how do we call them, and how do we execute them? So there are two aspects to it. One is called Aqua, one is Marine. So Aqua is a language, it's a compiler that takes the language, compiles it into an intermediate representation. And it's also a virtual machine, which actually executes this intermediate representation. And then there's Marine. Marine is general purpose runtime for our WebAssembly modules, which is based on Wasm right now. We're looking into extending it to Wasm time as well. And both Marine and Aqua are available in every Fluence reference node, which is the Rust node right now. It's also available in the browser. Now, Aqua is fully unconditionally available for the browser, for node apps, a variety of clients. Marine is fully available for multi-mode deployment on the Rust node, but only for single modules on the JavaScript clients and nodes. And we'll get to that in a little bit. But fundamentally, but it should be soon for just as capable as the Fluence Rust node. Basically, what it means, you can literally deploy WebAssembly modules for execution into your browser or your node client or your long-running node app, just like as you would for the Rust node. And so those both virtual machines are available, and Aqua really is about composition, and it's all about execution. And so we have Aqua, we have the virtual machines. So how do we actually hop through those different peers, and what happens when we do? And this is where we have to get a little bit into the foundations of the protocol and the implementation of the protocol. There are smart package, or smart packages. We call it the particle. And the particle, the smart package, basically combines data, the compiled Aqua script, and then some metadata. Forget about the metadata for right now, but basically your original data. So if you go back to our original example where we had this text colon +1 EthCC, right? And that's our original data, our Genesis data, and then we have the execution sequence where we in Aqua we said on node so and so execute the emoji injector service, and then find on another node execute the spell checker, and then on another node, which actually maybe have been the same node, execute the in parallel, for example, the write to IPFS, and at the same time delivery to that client. So what you have these topological hops across the network, and execution of these services on the particular node you reference. And basically every time you basically you hit an Aqua VM, it looks at the script of the intermediate representation of the compiled script, and it checks what's been executed, what needs to be executed. From there, it determines where to send the particle, either if it's on the same peer or to another peer. Once we're at the right peer where we have the service we're now looking for, we now execute that service on Marine. We update our data in the particles. We get a revised particle with new data and a new list of peers to go to, and a new workflow basically, or a new step through workflow remainder, if you will, that needs to be executed until you finally reach the end of the script. So this is actually a really, really interesting programming model. It's a data push model, and it's totally different from client server, and it allows you to use function addressability with all the great advantages of censorship resistance and a lot of robustness. You also get, it becomes very interesting and very easy, relatively cheap too, to ensure and ascertain availability as well as failover within the peer-to-peer network. Also, the model really allows you to very quickly and very cheaply exit. So if you host your service on a particular node and you don't like the service you're getting from this node, you literally just have to redeploy your WebAssembly modules to another node that wants to host you, and off you go. It's extremely portable, and the impact on your workflow is fundamentally zero, right? As long as you have somewhere a reference to the updated service location, you're good to go. Okay, so just a little bit more about tooling before we get to the code. I know you're all itching to get to the code. We'll get there. And so we have a Rust SDK. We have a Rust node. The Rust node is a reference implementation, and it's readily available for you to use if you want to run nodes. Fluence provides a whole bunch, so for the purposes of Hackathon, you don't have to, but you're more than welcome to do so. And we have Rust SDK. That allows you to create WebAssembly modules from Rust. And from those modules, you can build services. Those services have unique service IDs, and that gets you to these function addressable tuples we talked before about the BRID and the service ID. And the SDK also brings some additional capabilities, giving a very cool way on how to unit integration test the actual output of your Rust code, not just the code itself, but once you compile the code, which results in WebAssembly modules, you can now run unit integration tests on the very WebAssembly modules before you deploy them, which is actually super, super helpful. It also comes with REPL, so you can actually interact with your WASM models locally. We have Fluence.js, which allows you to create peers, clients, as well as long-running node apps if you want to. And they come, I guess I mentioned before, with Aqua VM, and right now slightly limited Marine VM, but that's going to change hopefully very soon. It also gives you capabilities from the Aqua compiler to create TypeScript and JavaScript wrap intermediate representations, which then in conjunction with Aqua allows you to expose JavaScript interfaces or TypeScript interfaces to Aqua to be used as if they were WebAssembly services. And they're just full-fledged services, just not WebAssembly. And this advantages, but it also requires you to run a particular node. And if you want to scale a node, if you want to parallelize this node, blah, 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 through Aqua, you would have to run multiple nodes. So the trade-off is if you want to be light as possible, serverless, if you will, you don't necessarily want to run a node, then you can just host it services. And for a variety of reasons, including some security considerations like signing, for example, signing, you might want to run the node or keep the client readily available. Aqua, part of the toolset, high-level language. It's a compiler. Compiler to high-level language compiles it into immediate representation, which then executes on the Aqua VM, which is the Aqua toolset, and there's also CLI involved with it. We're currently working on an alternative CLI, but the Aqua CLI is good to go right now. We also have a variety of libraries. The standard library basically is called AquaLib. We have Aqua Architecture, which is IPFS integration. We have registry, which basically helps you with the service discovery and publication. And for you to manage, and a whole bunch of more are in the pipeline soon, and obviously also looking for external contributors to help us build out the ecosystem. Demo and review. Yay. I hope you're ready. But before we get to the code, let's get to the problem. As Ethereum developers, you should be very familiar with the problem to tackle. Running L1 nodes is no joke. It's not cheap, and is quite intensive. So for a lot of dApp developers, it does make sense to run their own nodes, and instead they rely on blockchain gateways like Infura. And there's nothing wrong with that. Infura does a great job, but it does introduce a centralized choke point into your dApp. So the D in the dApp is, starting to look a little wiggly there. And so another question is, how do you deal with this? You can ignore it, obviously, which apparently a lot of people are doing, or you can try to find the way to mitigate that centralization to as much an extent as possible without actually ending up having to run your own nodes. And one way of doing this is verification by replication. So we can do this with Fluence as an off-chain solution. So basically what we're trying to do now is we say, hey, there's like multiple blockchain gateways, right? And for the same function call, for the JSON RPC call to the, in this particular case, Ethereum L1 nodes, we would all expect at the same time to get the same answer. So if we actually do the ETH_block capital number call, JSON RPC call, here it's just express its get block number to each one of those gateways, we would expect the same block number, block height at the same given time. Way to check how those gateways work and if they work properly. And however, In order to do this, we have the service. The service actually calls the gateway and brings back, in WebAssembly, brings back the result. And the services need to be hosted. And we obviously want to have a certain degree of availability, we want to have a certain degree of failover, and we want to have certain. So basically what we're doing in this particular example, we're deploying services to different nodes and then run those in parallel to get our result, our response to the requests from those different gateways. So with 3 services and with 3 gateways and 3 nodes, we expect nine responses, which hopefully are 9 out of the same block number at this particular given time. And then once we have each one of the nodes have those 3 calls, we join those responses, and then we apply a little bit of statistics. We use some frequency calculations, mode basically, and say, hey, how many, what's the most frequent response out of the responses we got? Out of 9, hopefully, and what's the end associated with it? And then we can provide a quorum threshold to our application. We say, okay, we want this point estimate of the block number, but we only accept it if at least 2/3, so 6 out of those 9 responses are converging on the same value, right? So it's quote unquote a point estimate. So basically verification by replication is one way you can very easily, very quickly, relatively quickly decentralize blockchain gateways and proudly retain the D in your dApp. And this is what we're going to go through. I'm probably not going to go through everything in detail, but I'll give you enough. We have a repo, and it's listed down here, and there's a big old README, and feel free to work through it. And there are suggestions on what to do and how to get involved. So we have a plan. What are our implementation requirements? How do you look at getting this actually done? So we just mentioned we need WebAssembly services, right? So we need to create those gateway providers, and we have to do those quorum calculations. I mean, that's sort of the minimum high-level stuff. And then we have these at least 2 services, and now we need to compose the services with the appropriate control structures in Aqua. Now, for those of you who are avid followers of WebAssembly, you already know WebAssembly modules are single-threaded, and they have a socket. So how do we call those gateway providers, and how do we get our code executed as quickly as possible? Because if we're too slow, if everything's sequential, we might very easily end up being on 2 different sides of the end of the block time, and actually legitimately get 2 different block heights. Unacceptable. So we need to parallelize. So we have WebAssembly, single-threaded, but we need parallelization, and WebAssembly, no sockets, and we need to call those gateway providers, like if you're a command link, to get our data. How are we going to do this? Well, as part of Marine, we created a punch-through capability from the WASI sandbox into the host, to the host. And that comes with permissioning. So if the host agrees to permission a particular binary, for example, to the WebAssembly module, then that WebAssembly module can utilize that binary. And this binary, in this particular case, is curl. So we can actually query our gateway providers with curl. We don't want WSS, for example. We don't want to have these long-running connections. We want it relatively quick, so otherwise the first block forever that blocks the Marine VM, blah blah. Very quickly, if you want to, you bring the whole network to a grinding halt, and that's obviously what we don't want. For you who have distributed systems, timeouts are your friends, right? So, but even one-shot calls are better than having to enforce timeouts and everything, which may not always work. Okay, so so implicitly, I just mentioned basically that Aqua is the provider of certain control structures that are not available in WebAssembly modules, which includes parallelization. So you have to rethink a little bit the way you design these decentralized or highly distributed services, because the parallelization of these services actually would happen at the Aqua level, and that has implications both how you express business logic and how you distribute, if you will, deploy your services and the number of services to the network. Because obviously you have to have, you know, the number of services available corresponding to the number of parallelization arms you want to have in play. Otherwise, you get a mix of parallelization or sequential execution, which may not bring you the time advantages you're looking for. Okay, so we had implementation requirements. What are our steps? There are obviously different ways of going through it, but you know, write our WebAssembly modules, interact with the gateways, configure and deploy those services, and then implement the Aqua service composition control script. Can do it different ways, but you do have to write the assembly modules before you deploy them and to the network. So there's a certain sequentiality required. Okay. So let's go to our code. So let me just show you something. We've been, I hope this is visible. So we said we're going to interact with Infura, Alchemy, and in this particular case, Link. And what we want to do is we're going to JSON RPC to do is just we would interact with our own nodes. Now, a lot of these services provide very, very cool higher level APIs, which are super cool, but they're usually semi-proprietary. So the one what's working in Infura doesn't work in Alchemy, doesn't work in Link, doesn't work in Beware, blah, blah, blah. So the common lingua franca, if you will, of EVMs is JSON RPC. So this is how we're implementing it. And if you, just in case you're not too familiar, you should be coming from Ethereum, but just in case I'm going to blow through it, this is what your request method would look like in JSON RPC. You give a method, you get parameters which are empty for each block number, of course, and IDs and nonce. And if you can literally call it with curl, which is what we're actually going to be doing later on as well, and then we get this result. If you should compare the nonce match and the result in this particular included latest block integer. So let's look in the left here in our overview, and let's just have a look at different directories we're using in order to get our stuff done. We have a directory called Aqua. This is where we have our Aqua scripts. We have a directory called Artifacts. This is where we collect our WebAssembly modules from basically the compile directories of each one of the Rust projects that end up creating these WebAssembly modules. We'll go into this a little bit later. We have some configuration files, some for local deployment, interaction with the REPL, and deployment to the network. We got some parameter files. I'll go in this in a little bit, but basically, yeah, I'll go in this a little bit. Some of them are to be used directly in Aqua function calls, and others are parameters we actually upload it to IPFS and then use in Aqua through the CID and the multi-address of this particular IPFS sidecar. And we'll get into why we're doing this in a little bit. We have a build script to actually compile our stuff so we don't have to do it. And then we actually have our WebAssembly modules. And let's just look at the multi-provider query module or Rust code. So this is our Rust code. And basically the core of it is get the number from whatever provider. Where provider info is a struct, which is the URL we're calling, and the name of the provider we're calling. So this would be, the name could be Alchemy, and this would be the Alchemy URL. Now, I chose semi-deliberately Infura, Alchemy, and Link for one of the reasons is not only do they allow us to call JSON RPC directly, they also have the API key as part of the URL. Except for Link, which doesn't have an API key, doesn't require an API key, and so we don't have to do some fancy header processing for tokens or whatever other alternatives there are to authenticate against those services. So if you want to use different services, you may have to slightly change the code in order to require header parsing to get your authentication capabilities and pass them on to curl. So, okay, so what we're doing, this is our method. So all this stuff we're doing here is we're basically creating the, reusably, the setup of the JSON document, which we turn into a string for the JSON RPC request. And then we actually just call it curl. So where does curl come from? We have this WebAssembly, and I told you this is punching capability through the WASI sandbox into the host system. How and where? Okay, if you look at the bottom here, we're basically, if you're familiar with Rust or C, C++, you realize this is an FFI style import of a link of something. And this something is actually a curl adapter. So where does the curl adapter come from? By the way, the mounted binary, this is where the punch through comes, and this is where we collect the results from the binary and bring it back as a result from this curl request call. So back to where does curl come from? So we have a curl, we wrote this curl adapter, and this is all there's to it. So basically, if you go again down here, we are linking to the binary on the host called curl, which takes an array of strings. That's it. And then we wrap that FFI imported, the FF imported binary call, if you will, and call it curl. Now we call it curl underscore request. Again, we take this array of strings, we return exactly the same mounted binary result, and we call curl just like we would here. So we compile this adapter code and we deploy it to the network with this module, and I'll show you this in a little bit, but let's just like look a little bit more at what we have to do in order to get our request. A service from each one of those providers. So we have the URL. So in here, private info just reply. We get the name and URL. We start calling curl with all these RPC commands. We get it back. We make sure that we don't have any errors in the return, because obviously this is fundamentally a non-deterministic call. We could time out. The provider may not be up, etc., etc., etc. And then if we actually do get what we want, which is the block height, we change it from the hex to a U64, and we actually create a JSON string with the key block height, and then of course the U64 being the block height. That's what we return. So we have more modules, but let's have a look at this module. So I showed you in actually, so in configs, we have this called config.toml, and this is where we list all those modules. So when we compile our WebAssembly, we, as I said, we collect them all in the artifacts directory, and this is our path into it, and all these modules are now available, enumerated and available in the REPL. So you know what, let's compile everything first, just so you know. And I'm running this script, and if you look in artifacts, we clean out everything, and now as we're compiling, as the compiler is running, as the compile script is running, we are adding all those WebAssembly modules back. And this is the build script actually, which is running, and nothing fancy about it. We basically, if we don't have the artifacts directory, we create it, and if anything's in there, we delete it. Not particularly efficient, but it helps for demos and workshops, and no surprises. We CD in our WebAssembly modules directory. This is where all our Rust projects are, which compile into these, which result in the compilation into these WebAssembly modules. And the key here is basically this, which basically is this, which Marine, which is the Marine SDK I mentioned before, the Rust SDK, it's Marine, and basically we specify to build that project, and make sure you specify release, otherwise you end up with like multi-gigabyte size WebAssembly modules, which you do not want to upload to the network. It's going to kill you on bandwidth, leave alone the hosts are going to probably reject it. And then we just copy it from the local compilation target directories back into these artifacts, just so have it all nice here, nice and neat. Okay, so now that we have that, what we can do is we can interact with those modules we compiled with the REPL. And for that, we need this config file to tell the REPL where to find what we need, one of those modules. And we now have a REPL. Okay, so this is probably not very visible for you. Let's make it a little bigger. So now we're in the REPL, in the Marine REPL, and let's see. That lists everything that we've exposed in our code. And I forgot to mention how we expose it. I'll go back and explain this in a minute. And so here are a bunch of exported functions. All the data structures, of course, and functions. So this is the curl request we were talking about. And this is the multi-provider query we were looking at. So let's see, I used it before. Okay, so let's call this multi-provider get block number, right? That's the Rust code we just looked at and compiled into this particular WebAssembly module, which utilizes the curl adapter. And we're doing this with the link gateway provider, which luckily doesn't use an API key, so I don't have to rotate anything or read that. And all right, moment of truth. Oh, look, it worked. Yay. And you never know when live demo. And we get back our JSON string with the block height as the key and our int. So it's not a hex, just exactly how we want it. So where does all this stuff come from the Rust perspective? All this stuff comes from, let's go back to this WebAssembly module we had before. See, every time, both in the device area, in the linking area, and the block function we created here, we use a macro called Marine. You can think of it as decorator. And this is what actually helps turn the Rust code and enforce the WebAssembly rules, because we're using WebAssembly interface types, which has limitations in the interface types, and also make sure that everything that is in that Marine block gets actually exposed to as a public function or method or data structure. So what you saw in the REPL, everything was prefixed with this macro. And just on the type side, everything WebAssembly is passed by value. So in Rust, there are no, within those Marine blocks, there's nothing complicated. There are no generics, there are no operator, there are no lifetimes. Passed by value. And only the primitive, fundamentally the data types, string, and blah blah blah. Nothing fancy, nothing too complex. And Marine makes sure. So if we, I don't know, put something more complex in there, it would complain bitterly. So if we put in a generic, for example, and then error, of course, it's no good. Okay. So we have a server that calls gateways and gives us back, hopefully, a block number. We need to deploy this service to the network. And I'm going to save ourselves a little bit of time here. We do this with the Aqua CLI. So first of all, Fluence provides a whole bunch of nodes that are, I mean, there are other nodes as well, but Fluence provides a bunch. And I encourage you, if you don't want to own, use the Fluence nodes. And you can actually do this with the command aqua config default peers. There are different networks. If you just do not use stage, you end up with Krasnodar network, or in this particular case, it was stage. And this basically are the peer addresses, right? This is the peer multi addresses, and back here, those are the actual peer IDs. And if you want to deploy a service, you need secret key. That secret key has multiple functions, including if you want to delete the service, you need to provide a secret key. And You actually can use authentication within the WebAssembly modules to restrict access to one function or many functions. And again, this requires the secret key. So create yourself one or more key pairs, one for each service if you want, or just one for all services. Obviously, that's risky. If you lose the everything, you have to redeploy all your services. You can't even, you may not even be able to delete them, or somebody else already deletes them for them. So there are some trade-offs to be had. And then we use Aqua to deploy the service. And the service we just deployed was called multi-provider query. Remember, this is what we called this was the WebAssembly module. This is what we called it, right? And this is secret key. You got to put in and just a thing in the log level to keep it nice and clean. And the response you should be back is that we're uploading a module, we're uploading another module, two modules. Why? Remember, we needed the curl adapter to empower that multi-provider query WebAssembly module to actually make the calls. And then we end up with a blueprint. Blueprint is basically the hashing, a particular way of hashing all the modules you uploaded. And then you get service ID. So the blueprint ID, if the blueprint ID is static, as long as you don't change your WebAssembly code or your WebAssembly modules, you end up and you upload it in the same configuration, you end up always with the same blueprint ID across any peer you deploy this particular service over and over again. It's always the same. However, in order to actually instantiate those services and run them, you need a service ID, and that's a unique, basically, it's UUID, and which is unique and associated with those blueprints IDs. So you basically can generate multiple service IDs against one blueprint ID, and you have uniqueness to address your instantiation of that particular service. So we have two modules. Where do those two modules come from? Configuration, deployment. So this is a deployment config file, and it has multiple modules in this. So we can, each one of the sections can be deployed independently of the other ones by just simply specifying the name in the service we want to deploy. And this was the one we wanted to deploy, and it's comprised of two WebAssembly modules. We are basically packaging and quote-unquote linking once they are deployed onto the host, which is the curl adapter, which is then used by the multi-provider. So if you actually make sure that the order is right, you have to have the curl adapter binary first. And if we specify the curl adapter, it has a binary. So this is the mounted binary we're using, and you can check on the Fluence nodes. If you go, if you shell into the node, you run which binary, which curl. That's where it's user bin curl. Great, and it's available in all Fluence nodes for sure. And that's the command we're using. And the rest of my memory allocate where the path is in artifacts. So now you see why we moved everything to artifacts, because it's just a lot easier to deal with. And then, of course, this is the multi-provider query we were using. Again, we set the memory, and of course, we don't need any mounted binaries because there is no access directly from this multi-provider query WebAssembly to the host. It's done through the curl adapter. Okay, so we get this service, we deployed those services, and now we actually would like to check if those services are working. We actually now get into writing some Aqua code. And in this particular case, our very simple one to basically, we just want to get block heights, right? So we give a bunch of provider info and function addresses. So we had 3 providers, right? And the providers was the name and the URL, remember? And we had 3 nodes. So we have 3 nodes, peer IDs and service IDs, and we want to get back the EVM result, which is what we're looking here. Basically, just tells you the provider and just a standard error. And it's an array thereof. So in our particular case, when we run it, 3 providers, 3 nodes, we should get 9, an array of length 9. And basically, we create here, right? What we're saying here is for each of the addresses, function addresses, services deployed on that peer that hosts this particular service, create this binding the multi-provider query, which we specified here, which remember, get block number. We looked at this at the very beginning, and now we're back to here, which corresponds, of course, to the function and module specification in this particular module, right? So we basically say, hey, create this binding, and we run all this parallel. We do by specifying par here. And so basically for each provider, for each service available, we run in parallel on each different node the provider info, basically run the request. And then we get some results back. We don't really need that, and we return it. So blah, blah, blah. What does it look like? Okay, first of all, this is very, very ugly, but it's very illustrative. So we say Aqua run, and then we just select appear on the network. We on the namespace of the network we're looking at. We use stage in this particular case, and we basically say, hey, compile this Aqua, and then we say, hey, call this function with those two arguments, and then we specify those arguments because they are JSON. Specified in JSON, we break them out separately, and it's of course not particularly nice, but here we say do this with your API key, do this blah blah blah, and run this with of those different service implementations. Now, of course, we don't really want to use those API keys because we're not going to get anything. So let's see what we're getting when we're calling this, because obviously we're not going to be authenticated to. So you got to put in your own API keys. So link, I said, didn't require an API key. So we said, okay, message expected here, message error, block height, error, block height, error, block height. So this is all consistent. All the block heights are the same. So even though we didn't get authenticated, at least link across the 3 different nodes gives us the same block height, which is somewhat encouraging. If you actually, again, if you update this with your API key, you actually get 9 results. And I'll show this in a little bit because I'm going to abstract away over the API keys. So again, I don't want to have to redo my keys all the time for those providers. Okay, so we're getting close to the hour, so I want to wrap it up. There's a whole bunch more modules. Have a look at the README. But what I do want to show you is the end now. So here we got sort of a full-fledged everything Aqua function, which takes both actual arguments. So the provider info we pipe in as arguments just like we did before. And the reason for it is IPF is public, so I don't want to put my API keys onto IPFS necessarily. So I just rather use that. But then all the other parameters we saw before, we actually upload to IPFS. We get CIDs back. We know the email address of the IPFS node, which is sidecar to some node in the Fluence network. We then basically call IPFS, get those IPFS documents, map them into variables like we did before, and then we run our whole gamut. And here, this is where we call IPFS and we get we get the addresses back just like we had before, right? Function addresses, and then we also now have a quorum service which we already deployed and some utility service we deployed, and the quorum service we get the function address right here, and then basically we move in, and again just like before, we now get our 9 responses back hopefully. So we do it again in parallel. And now here we actually start calculating the quorum. And I didn't show you the service, but you can figure this out on your own. And basically what we're saying here is calculate the quorum. If we do have a quorum, then everything is fine. If not, we return no quorum. And we do this here. We actually add it in there, which we pipe it as a raw parameter, our quorum threshold. And this is where we make the distinction right here. And then we also are interested in, so if we just run this up at this point, you basically would get what, I don't know, 9 out of 9 the same, or 6 out of 9 the same, but you have no, it just tells you what the frequency distribution is basically of the quote unquote winning response. And that's okay. But if we want to start building trust profiles over different providers and different nodes, for example, we actually want a little bit of information. And get this information by adding this particular sub portion here. So basically what we're saying is like, hey, we have this where the utility service comes in, convert this JSON string into just get me the block height integer. And if that integer is not equal to the mode, then we have a deviant. And if we have a deviant, we want to print that out. That's what we're doing here. Of course, the printout is just a placeholder process. You could save it to IPFS. You could save it to Ceramic for further processing. Update the running tally of accuracy or inaccuracy of a particular service or node. And we do this as, in this particular case, as a coroutine. And we do this as a coroutine because in order to print, you can fundamentally only print on the peer you're calling from, not the peer you actually executing on those services. And so basically what we're doing is here, we go from the peer we're quote unquote on, we call from, and then we make a topological switch to this peer up here for each one of those addresses. And then we basically switch back to our original peer and as a coroutine, so we don't incur any major time penalties. And then we just print out the quorum, basically the highest frequency of the block height that we've encountered, and whether or not we accept this quorum. So let's execute this real quick. And this time, all right, so just as we discussed before, we're now going to run the last Aqua function, and that's the Aqua function with the CAD arguments primarily and a couple of raw arguments. And just to go back, we had these, this is our mixed parameter file now, which we data path, and this is what it looks like. So instead of the node and peer IDs, we have CIDs and multi-addresses. And for example, the quorum addresses, which were here, now, of course, look like this. All right, so those were our provider arguments. Remember, we said we're going to keep them raw because it includes our API keys, and IPFS doesn't inherently provide privacy, so we said we'll keep it raw. CID, 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 3 different services, and then we have the arguments, the raw arguments of our IPFS service. And the threshold. The threshold probably is actually a candidate for IPFS because the immutability around the threshold, if you wanted to have some provability guarantee that you didn't change your parameters. So that's for the particular outcome, that would be actually kind of helpful. So I should have thought of that, and I didn't. I apologize. Anyway, so in your own attempts, replace that parameter. So let's run it. And with Zoom runners, it might take a little bit longer than I'm hoping for, but we should be in good shape. Yes. So we remember we had 9 calls in total. Our frequency is 9. This is our block, so everything's fine. Our quorum is satisfied, and we're in good shape. If that hadn't been the case, then just before we would have had different, threshold settings and different quorum acceptance. And if we had different frequencies, then relative to threshold, blah, blah, blah. Just as, anyway, it's the same thing, just we're now using IPFS arguments. That's really CID arguments. That's really the only thing. And we're resolving the IPFS reference content addressable documents in the Aqua function. That's all there's to it. And that, of course, has a lot of implications. So aside from, as I mentioned before, there's the immutability associated with the CID. So if you want to share your parameters or reuse them later, you have immutable reference to them. But you actually can start building IPLD type data models. So we actually could build link parameter settings, and obviously create much more complex data models, which we then could very succinctly and immutably, because of CIDs, feed into these functions. All right, so this was it for the code. Thanks for bearing with me, and everything actually went off without a hitch, so that's pretty cool. Let's just finish up the presentation. We're getting on the hour here. So we have a few available integrations available, including IPFS, which we just discussed, Ceramic. We have a near integration, which easily extends to EVMs in general, and Web3 libraries. We have additional building blocks around adapters, integrations, NFTs, and a lot of it coming, also DC and DIDs coming from the community, so have a look. And now, ta-da, the bounties. So we get two sets of bounties, one best use of Fluence off-chain compute and best peer-to-peer protocol using Fluence. And each one of them have two sets of prizes, €1,500 each, twice. One for the best in person and one for the best online submission. In terms of ideas, any ideas obviously, go for it, pursue it, amaze us, dazzle us, and have a lot of fun doing it. If you're a little light on the idea side, things like moving complex computations for a DeFi NFT project to off-chain Fluence network, that's obviously something. Keep the D and the dApp, just keep it alive, it's important. Build data processing engines for IPFS and Filecoin, either from the blockchain to or from the data back to on-chain, whether that's an Oracle or some other triggers. It's up to you. I'm pretty enamored with CIDs in functions. As you can tell, you may not think it's a big deal. I think it's really cool because of all the benefits I pointed out earlier. So you build more complex data models. You may actually want to indexing, because every time you change something, you need to re-index IPLD. And for that, you can actually use Fluence. So it comes full circle. So this would be also something I think we'd be looking in very interesting. It's a very interesting project, particularly if you can start using, because if you have these complex data models, they're not just succinctly represented as a function argument, but also in smart contracts, right? I mean, so you can very easily, very cheaply anchor very complex data models and really push on the provability aspects of it. And finally, another one of our favorites is utilize DAO proposals to trigger off-chain compute events with Fluence. So the idea here is as you have some off-chain compute requirement as a result of a proposal being accepted or possibly rejected, and that compute should be triggered by the outcome of the voting process. So one way you can do this to really keep the automation and working is you attach or you embed the Aqua decompiled Aqua script in your proposal, and upon execution or upon vote outcome, the script now gets executed. And there's different ways of doing this. Reach out if you want to, but keep in mind the script itself could be uploaded to IPFS. You have a CID and the content addressability to the script, regardless of where you're calling from, right? And then all the compute models you're actually using, all the service models themselves, actually can be also on IPFS or Filecoin. So you also have content addressability, and you have the immutability of the actual services. So you could have the script that actually loads and eventually unloads those services required in order to the execution. And I'm pretty excited about it. I think it's a really, really cool use case. And if that's something you're interested in, reach out. We can go through it, and certainly look forward to building it. And before we close out, we have a website, we have GitHub, we have Discord, we have Telegram, and of course we have Twitter, and we also have a job opening. So if you're interested in particular around Rust, if you're interested in building nodes, if you're interested in compilers, if you're interested in language development, Aqua itself is developed in Scala, for example, any of that, if you're interested in peer-to-peer protocols, if you're interested in developer relations management, so there are some core engineering and some related and some non-engineering, including marketing, product, reach out and get in touch. And that's it. So thank you very much. Thanks for having me. Have fun. good luck, and looking forward to some great submissions. Cheers.